Okay, so let's kind of start to work through some of these problems. So here's kind of the schedule as it looks right now. So it's going to take us a while to get through these problems because there's generally a lot of questions and things we need to discuss.
Yeah.
So then we'll start this lab today. We'll finish that up tomorrow. We'll review on Friday. The energy test is going to be on Monday. Okay, so that's kind of the schedule as it is right now. All right. So let's talk about number 2A, because if 2A is wrong, everything is going to be wrong. So there's two ways that you can approach this particular problem, how you start it. So one option is that you can go an energy perspective. And you can go, oh, okay, this thing has a certain amount of kinetic energy because it's moving, right? It's already moving at 1.2 meters per second, okay?
Mm-hmm. Yes, I'm sorry.
And it has some UG because of the fact that it has room to fall, okay? And at the bottom, the sum of those two values is just going to be what? At the bottom, what's the only type of energy you're going to have? Kinetic. So you can call this K naught, and that's going to be your final kinetic energy. Okay? So that's one approach that you can take, and that's like a bigger picture. That's what I'd like you to be able to do. Go, oh yeah, right. It has UG, it has some kinetic. So that's going to be 1/2 mv squared. Now, the mgh part. The h part is where you have to use that height equals L times 1 minus cosine theta. Okay? You've got to use that to figure out how high above that equilibrium point that bob is located. Then, that's going to equal some final kinetic energy of 1/2 mv squared. Now, if you start with this approach, then you can go, oh, right, cool. I can actually cancel out all the masses because those aren't there. Or the same on both sides. I can multiply by 2. And I can get v squared plus 2gh equals v squared, otherwise known as
That equation.
that equation.
Oh, yeah.
Okay? So you can either look at it, if you start with the energy perspective, you end up with that equation. Or you can just start with that equation. Okay? But that answer to 2A should just be a little bit above 4 meters per second. Okay? Just a tiny bit above 4 meters per second. 3 significant digits.
Like
Okay?
5.
Huh?
Like 5.
No.
It's a little bit above.
No. I'm talking like a tiny,
Like
tiny,
2
tiny,
cents.
tiny bit above 4.
Like 2 pennies.
2 pennies?
Yes. U.S. Not Canadian. Okay?
Spring?
So, yeah, 2. Tiny, tiny bit. So, then, visualize what's happening on B. So here's one that's at rest. This one is going to swing in, it's going to hit, they're going to move off together. It's a California problem. It's a momentum problem. Okay? So obviously your answer to 2B has to be less than your answer to A because you've combined the masses together. Okay? So your answer to 2B should be, this is an ish, this is a big ish, but it's around 3 meters per second. Okay? Now, visualize this. These two are going to swing off and go up here together. So, again, there's a couple of ways you can view this problem. One is that you can say, okay, when it's at the bottom, when those two move off together, it has all kinetic energy. When it reaches the top, what's going to happen to all of that potential? What's going to happen to all that kinetic energy? It's going to be stored as
potential.
UG, right? So you can go, oh, that's 1/2 mv squared equals mgh. You know how fast they're moving when they swing off together. The masses cancel out. You know what G is. Boom, find your height. Then take that height and plug that into here. And then it's the same length, so then it turns into an algebra problem. So then you've got to like distribute the L,
Cosine.
get everything by itself, take the inverse cosine. So if all goes well, that angle on 2D should be in the mid-40s. Okay? Should be in the mid-40s. Pop,
What is that equation? L times what minus cosine?
L
times
times
1 minus cosine
minus
theta.
cosine theta?
It's on the sheet.
Yeah, but it doesn't look. It looks like I don't know.
You used the one.
No, I've used one, but it looks like an L.
Oh, no. No, that's why that
And
L
I
is on
thought
the
the
outside.
last time we had the equation, it was L minus L cosine theta.
I just factored it out. It's the same equation. I just factored
Oh,
out the L.
Okay.
It's the exact same equation.
What?
Because if you distribute the L, then you get L minus L cosine theta.
Okay.
So it's the exact same thing.
Yeah.
I actually, this one's usually a little bit easier.
I'm
Okay.
martyred.
Why does it?
Is everybody cool with that problem?
Yes.
Okay.
Sorry.
Now, on the next problem, the joules on B, this is an ish, should be around 10. And the energy on C should be around, this is an ish, 40. Okay, that's an ish.
For which
This
one?
on
Three.
3C,
3B is like around 10 and 3C is like 40.
around 40. So what you got to do on 3C, take the energy that you have found in B and add that to that additional energy that you're going to have because it's moving. Okay? Everybody cool with that one? Now, let's talk about the satellite problem. And yes, I promise you, you're going to have a satellite problem on the test.
Lord have mercy.
I promise you.
Yeah, I'm confused on I, bro. You know.
You're confused on I. You got to the second to last question.
Okay,
Yeah, bro.
so let's talk big idea. So this is kind of your ultimate real world situation. You work for a rocket company, okay, satellite company, you got to deploy this satellite. You got to figure out what do we have to do to make this rocket spin, okay? And that's the whole idea, is that imagine that, like here's the sun, and I only have one side of the satellite facing the sun. Now, keep in mind, you're up above the atmosphere, okay? There's nothing to filter the sunlight. You are just being bombarded, boom, straight energy. So what's going to happen is that if you don't make this thing spin, one side of that is going to get really, really hot, and the other side is going to get really, really cold. So if you've ever seen the movie Apollo 13, it's a very subtle part. But after the explosion, that's one of the things they talk about, is that how do we get this thing into what they call a barbecue roll. So it's almost like a rotisserie chicken. Okay? You obviously don't want it spinning so fast that the astronauts are getting sick. But what they want is a slow, gentle roll so that you get an even heating of the spaceship. So you don't want one side getting really, really cold and the other side getting really, really hot. So you want this thing to spin very slowly. So it's going to start off at rest, and you're going to make this thing spin at 32 revolutions per minute. So you got to convert that into radians per second. Hold on to that number because you're going to need it later on. And then you're going to have to find your alpha. So that angular acceleration on 4A should be 0.0112 radians per second squared. Okay, because if that is wrong, literally everything is going to be wrong. Okay? Promise you. Everything is going to be wrong. Okay.
That'd be tragic.
Now,
That'd be so tragic.
when you get to B, you want to calculate how much force is exerted from each rocket engine. Okay? So you got to go torque equals two things. It equals force times radius. It equals I alpha. So you've got to calculate the moment of inertia of the satellite as it's rolling on its axis, cylinder. You know your angular acceleration from here. You know the radius. You're going to find the total force that has to be exerted. and then you divide that by the number of rocket engines that are available. Okay? So that answer to 4B should be close to the legal drinking age in the United States.
Vitor.
Okay.
No.
Oh, you sold.
I sold
Oh,
What did you get, Vitor?
71,
Vitor, what did you get?
like 80.
That's the total force. You have to divide it by 4 because you want the force from each rocket engine.
Oh, okay.
Oh, that's an easy. That's a lot better. But you got to go through everything
So
else.
is it?
now.
So it's like 19.8.
Well,
Oh, you sold Vitor.
because the force should be a little bit above 80.
Just 20, that's it, no other secrets?
Your total force that you need should be a little bit above 80. So something got twisted somewhere.
Yep.
Okay, now, when you get to C,
Write that down.
so C is probably the most relevant calculation. So here's the deal.
What?
If you're launching satellites, guess what? You have to be very concerned about the payload. Because if it's too heavy, guess what? You can't get it off the ground. It's kind of an important thing. So you're tasked with figuring how much mass this thing has to carry. Now you don't want to screw it up and go, oh, we'll just round up to 100. We'll just pick a number. Call it 100 kilograms, okay? Well, that might be way, way, way too much. And you don't want to go, oh, we'll just put a kilogram in there. Well, if that's too little, then here you've launched this multi-million-dollar satellite. You didn't put enough fuel in each rocket. It doesn't spin fast enough and you toast it, okay? And they're gonna come back to you, hey, what happened? I don't know, 1 kilogram sounded good, okay? Well, idiot, it's not spinning fast enough. We've just toasted a multi-million-dollar satellite. Thank you very much. So what you wanna do on this one is fundamentally, you have to change the momentum. So, force times time with rocket engines. And you all are used to seeing that as mass times delta V. You're used to the mass staying constant and you're changing the velocity. With rocket engines, you switch it up. It's still force times time, but then it's changed in mass times the velocity. Then you want to find your change in mass. So that answer on 4C should be between 10 and 20 kilograms. Okay? Now, when you get to D, okay, on D you want to calculate the angular, or the total amount of energy. So that's going to be a pretty big number. Should be something times 10 to the 5th. Okay? On E, you want to calculate the work. Now, here's the easiest way to calculate the work. Work, generically, is change in energy. So what's the initial rotational energy of the satellite? 0. Okay? You know the final rotational energy? Yeah?
Yeah.
So that change is equal to the work. Okay? But then it asks for the work done by each rocket engine. So then you got to divide that by 4. So your answer to E should be something times 10 to the 4th. Then on F, that power calculation is work divided by time. So that should be something times 10 to the 2nd. So D is to the 5th, E is to the 4th, E is to the 2nd. Okay? Now, when you get to G, you want to calculate the kinetic energy of this satellite as it's going around. Obviously, that's going to be a really big number because it's moving really fast. So you got to go kinetic energy equals 1/2 mv squared. But you've got to calculate the velocity of the satellite as it is in orbit around the Earth. So that's where you've got to go old school, big G M over R. You got to calculate that velocity. Now, if you want to get clever, this is actually the square root, but then you end up squaring it. So you could just not square it. Because if you square it and get the velocity, you're just going to square it again
Yeah,
and
it's close.
you get the same number.
These two don't
So
matter.
remember, what is the exponent on any orbital velocity in near Earth orbit? 10 to the
third?
what?
Third?
10 to the third. Okay? So your answer to G should be something times 10 to the 11th. Okay? Pretty big number. On H, you want to calculate the orbital period of this satellite. Again, if you're in seconds, what's the order of the magnitude in seconds in a near Earth orbit? 10 to the third. So your answer to H in seconds should be 10 to the third. It should be about an hour and a half. Okay? That's an ish, but it's going to be about an hour and a half. When you get to I, you want to calculate the angular momentum of the satellite. So you got to use L equals I omega. Now, what you have to do here is the trick here is your omega. So your omega is going to be 2 pi divided by however long it takes for that satellite to go around the Earth. So you got to use that time that you found on H to get omega. Now, the I is going to be different. That I is not the I of the satellite as it spins on its axis. That I is the satellite being treated as a point mass as it goes around the Earth. So that one you're going to use mr squared. And you got to use, and don't use the radius of the satellite. That's how far it is from the center of the Earth. So by far and away, your biggest answer should be your answer to I, and that should be something times 10 to the 14th. Pretty big number. Now, your answer to J, because you want to find the rotational kinetic energy. Okay, so let's look at this. Your answer to J is the exact same as your answer to G. And here's the reason why. Okay? Kinetic energy is 1/2 mv squared, right? Okay?
Mm-hmm.
And rotational kinetic energy is 1/2 I
W squared.
omega squared. So look at this. If you treat it as a point mass, I is going to be
V squared.
mr squared. If you treat it as a point mass, right? Okay? Well, for omega, what can you substitute in for omega?
V
R,
squared.
RV.
V squared over
V squared over.
R squared.
So what happens?
And it just
R
equals
Your
out.
r squared cancels out and you get the exact same thing. So you can either find your omega, which you already have because you already have the number, and multiply that by mr squared, but anyway, so no matter how you do it, that should be 10 to the 11th. On the test, I won't make you do like the velocity calculations. Okay, I did that just to kind of get you, just kind of a review to keep you fresh with that. What I'm going to expect you to be able to do is basically through F on the test. Okay, so on the test itself, I'm going to stop at F. Now, on the final, the whole thing is fair game. Okay, but on the energy test itself, I won't go anything past F. Okay. On 5, again, if 5A is wrong, everything is wrong. So your answer to 5A should be around 2.5 meters per second. Okay? Pretty close to that. And this is one, and I promise you, you mark my words, I promise you there's going to be one like problem number 5 on the test. You mark my words. Okay? So here's what you've got to do. Start with UG at the top, and you remember this in terms of the lab that you're going to do today too. You're going to start with UG at the top, and that has to equal the sum of two things, the KT and the KR. Okay? That's what you got to do. KT, KR. Now, here's the deal. That KT is going to be 1/2 mv squared. That's 1/2 I omega squared. So you got to do two substitutions in here. what are you gonna substitute in there for I?
1/2 mr squared
Why?
because it's a cylinder.
Because it's a cylinder. What are you gonna put in for butt squared?
V squared over r
V
squared.
squared over r squared. Vtor squared over r squared. So that's going to allow you then to cancel out the masses and all this other stuff. So now your answer to C, and again, keep this in mind when you do your lab. Your answer to C is going to be what would happen if that ball just fell straight down. Okay? Just went doink, here you go, that's it, just fall straight down. So that answer to C should be bigger than your answer to A, because it's just like Vitor's inheritance. On C, Vitor gets all the money because he's an only child, okay? Doesn't have to split it. On A, he's splitting it between him and his little sister, okay? So that's why that answer to C has to be bigger than that answer to A, because then you're not splitting it, okay? Are we good? Anything else? Going once? Vitor?
Just what is 4F, like what is it around?
4F?
Yeah.
I also did
Between 100 and 200.
where
I-
I set up numbers where I had the unit split to three different tables. Between 100 and 200.
Yep. On 4F, yes, between
So
100.
how do we find the work that's done?
Afterwards.
On which
Each
one?
rocket on 4E.
Okay, your work is just gonna be the change in your rotational kinetic
So
energy.
it starts at 0 and then.
And then it
it's just-
ends up at your answer to D,
Yeah. Oh, answer to D?
because that's your final
Which is?
rotational kinetic energy.
Oh, yeah, D. Okay.
Yeah. Is
Yeah, okay. And then, oh, that makes sense.
But then you went, so that's the total work that has to be done.
Yeah.
Then
And
you
have
divide
to
that by
divide it the
4.
amount of rockets.
Yeah,
Yeah. That makes sense.
makes sense?
is that 80.64 better for that 4B?
For which one?
4B, and then divide that by 4.
Yeah.
Okay.
Yeah, that's a lot better. I don't know how you got,
I don't think I squared.
that will happen.
So anything can be on the final? When is the final?
We're done on Wednesday.
Mm-hmm.
The final will be on Monday. And then you have a 2-day lab final.
Lab final?
But it's pretty fun. I don't set it up to be stressful. I set it up to
Okay.
be fun.
Yeah. We have like really different final scheduling at Mayself, right?
I don't care.
Okay.
Oh no.
He
I
does
don't.
not
As long as it
care.
doesn't interrupt.
I don't care.
He does not care.
Lord.
I cannot begin to tell you how much I don't care.
Oh,
Lord.
yeah, it shouldn't get in the way though, so yeah.
Yeah, I don't care.
Wait, what happened?
We tried that once.
It would-
It was a failure. So that's why we don't do it anymore.
I have one more question.
Oh God, on Friday. What? Ask Vitor.
So, Victor doesn't know what he's talking about.
Man,
So
I
for
got more done than you.
2C. Is that just the energy?
It's
that-
just the difference between the energy that it has before the collision
And energy
and the
after.
energy after.
So you just take that velocity and then mass and plug it in.
Yeah.
Yeah, but you're gonna have two different masses and two different velocities.
Yeah. Uh-huh.
Because the first energy is the single bob by itself.
Yeah.
Swing.
And the second one is the combined masses with that new
Yeah.
velocity.
You just
Yeah.
Yeah.
I thought you just spoke
Right, right, right.
Okay, anything else going once, going twice, so?
per second for power.
No
Okay.
chance.
Got it?
Come on, Vitor, it's not rocket science.
Okay,
This is.
so here's the main idea. You're gonna set up a ramp between 20 and 30 degrees, I don't care, okay? It's up to you. And you're gonna take a tennis ball, and you're gonna hold it up, and you're gonna let the tennis ball roll, and oddly enough, it's gonna hit the ground, okay? So when it's up here, what does it have? Potential. When it hits the bottom, it has
KTK.
KT and KR, right? So here's your task. You're gonna figure out all the information that you need to know about this tennis ball. First off, you can treat it as a hollow sphere, so you know which moment of inertia equation to use. you figure out how you're going to measure the quantities. The mass, I'll give you a scale, okay? Not a big deal. But you need to figure out how you're going to calculate the moment of inertia of this sphere. Your group, and you're only going to hand in one of these per group, okay? So only one per group. I don't want to be impressed, okay? If you want to type it, great, or if not, just...
I'm not typing it.
Okay, then you can lay it all out, but you lay it out very thoroughly, okay?
You guys want me in charge?
Yes, please.
Very thoroughly.
Yes, please.
No.
So I don't
You didn't have
care
it last time.
how high it is when you drop it. If you want to start it all the way up at the top and have it roll all the way down, I don't recommend that you start it really low and just do that, okay? Because it's going to be really tough to. So here's what you want to do. What you want to figure out is the total amount of kinetic energy that it has at the bottom. And then compare that to the theoretical
It's
energy
sliding.
that it has up at the top.
Sliding.
Okay? Which means you have to find a way to calculate KR, KT, and UG. Now, let me give you some hints.
Okay, UG isn't too bad.
Well, where are you going to measure UG from?
The top.
Are you going to measure from the center mass of the ball, top of the ball, bottom of the ball?
Center mass.
Hold on.
Bottom.
Okay? Because when you talk about the UG, it has to be relative to a point. Okay? So, if you're going to measure from the center mass of the ball, then when it gets down here to the bottom,
It wouldn't have hit the ground.
then it's not going to be, you can't measure from the ground. Okay? So that's just something that you need to be aware of. Okay? So I don't care where you measure from. Bottom, top, middle, I don't care. But you need to keep in mind how that's going to impact that UG value. Okay? You got to be able to calculate that linear velocity. Okay? Well, obviously, when you let go of it, what's it going to do?
It's gonna roll.
Rolling.
It's going to roll. It's going to speed up.
It's gonna roll in.
Are you going to have linear acceleration?
Yes.
Or you can have angular acceleration?
Yes.
Which one do you think would be easier to measure?
Linear.
Linear.
Keep that in mind. Okay? I would suggest you do at least 5 trials. Okay? Be consistent. Now again, here's your parameters. When you look at this grading rubric, which as Louis pointed out is very thorough, okay? So that there's no ambiguity. So, name of the group, come up with something clever, okay? Just don't say the guys, okay? Make me laugh. Come up with something
The
clever.
boys.
Okay? Oh, that's even better.
It's
the boys.
great.
The boys.
The soccer
with a
boys.
D.
The boys.
Okay? So, I tell you, you're going to treat the ball as a hollow sphere. Set the angle between 10 and 20 degrees. I don't care. Pick one.
Right.
If you want to measure if you want an exact measurement, let me know. I'll bring my phone over if your phone has an app. So, here's what's going to be handed in. Derived equation for the theoretical velocity at the bottom, assuming it has both translational and rotational kinetic energy. That is no data. It's just boom. V is going to equal boom. Okay?
G squared.
Potential energy at the top. That's worth 2 points. If you can't handle that, there are other issues. Theoretical translational kinetic energy at the bottom, theoretical rotational kinetic energy at the bottom, experimental acceleration as it rolls down the incline, final translational velocity at the bottom, experimental translational kinetic energy, experimental relevant data and diagrams, answers to the spring question. Here's the spring question is up here. Okay. Calculation of energy lost, value and percentage, and then a summary. Sources of error, and so help me with all of my being. If you write as a source of error human error, I am going to wad up your paper and throw it away. Okay?
0.767.
Ain't happening. Do not put human error. That is the lamest excuse that exists. Okay? What I want you to think through is, let's say that you have you think it should have 0.2 joules of energy at the bottom. You measure it and you get 0.3 joules of energy. where could have you screwed up in the timing, the distance, whatever? How did you gain 0.1 joules? Okay? If it's less than that, where could have that energy gone? What could have you done wrong to explain that? And again, go back through and look at what you're measuring. What physical quantities are you measuring, and where is the potential source of error in those measurements? Okay? That's what you want to think through. So, on all of these, what I would recommend, make this simple for me to grade. Okay? So like on this rubric, just say, boom, here's my theoretical. And again, this is a summative, like lab final. I want to be impressed, okay? I want to see, here's the equation. I want to see, here are the numbers with the units. Here's our answer, okay? Do not just write down random numbers and think, oh, Burkamp is going to know what's going on. Your guiding light is that someone should be able to take this who has a rudimentary understanding of physics and follow what you have done, okay?
Yeah.
That's your guiding light. It isn't, don't write this for me to grade it. You write this that you're trying to explain what you're doing, and someone should be able to replicate your results, okay? So let me give you a hint. If you say, oh, measure a height of 0.1 meters. Okay, cool. Where? Are you measuring 0.1 meters here? Or are you measuring 0.1 meters there? Okay? When you say set the ball on the table, well, where are you setting the ball? Okay? If you just tell me to set the ball on that board, I'm going to pick any point that I want. Okay? Be specific. When you say put the ball at 0.1 meters, are you talking about that's where we're going to put the front edge of the ball, or that's where we're going to put the center mass of the ball? Okay? If you tell me to put it all the way up at the top, okay, that's cool, right? Then tell me that. And again, when you tell me to put it up at the top, you want the back edge lined up with the top, you want the front edge lined up with the top, which isn't going to go very well because it's just going to do that, okay? So, but that's what you want to think through. When you're writing up that procedure, it's going to say, this is what we did. Be careful, because that's the only really procedural part that you're going to have, is what angle are you going to set it at, where are you going to start the ball, are you going to let it roll all the way down to the ground, or are you going to do a setup like this where you have a book or something where it's going to hit here, are you going to have it go off and go all the way to the table? Those are the things that you need to think through, and those are the things that are going to make a difference in your UG and your distances as this thing rolls. Okay? All right, I'm done. So you got today, tomorrow, so no, you don't have any homework tonight. Some of you are behind on some work, and I want that caught up.
I have it.
I know.
Okay.
Yeah, Mr. Burkamp.
Assignments for